So good afternoon, everyone. Welcome to this other special edition of the NITheCS Colloquium. And this afternoon, we are very pleased to have Professor Stéphane Vinatier with us. Stéphane is based at University of Limoges in France, where he's a professor of mathematics. Yeah? And he works mainly on algebraic number theory, but also on other things like combinatorics and linear algebra. Yeah? Sorry, I need to read. I've forgotten. And he collaborates with our colleague Sophie Market. So Sophie, thank you very much for making sure that Stéphane is here with us at the beginning of 2025. Yeah. Stéphane has a particular interest, maybe two, I think, on mathematics education. Yeah, and he was instrumental in directing efforts in France. And I'm sure that our colleagues learned a few tricks from him for our mathematics education. Yeah, but he also enjoys mathematics diffusion. Yeah, so and I guess this is part of what we are going to listen this afternoon. Yeah?
Sure.
And I also like reading in your bio that you like teaching latex. You know, if you would have added, I like teaching Emacs, you would have been my hero. Okay, but thank you very much for being here. Thank you also to the online participants, and apparently the painter might be in the audience as well. Yeah.
Sure.
So Stéphane, please, over to you.
Okay, thank you very much, Francisco. Thank you for the invitation in this wonderful place. It's really a great pleasure to be here, very far from France, but a very nice trip. So as you see, I'm going to speak about an interaction between arts and mathematics. I think interactions between arts and mathematics are always very specific, so I will only speak about one specific interaction. So the art part is by Reg Alcorn. All the paintings you will see are by this artist, Reg Alcorn, who's normally online with us, but I don't know if it's the case. Oh, so let's start with one of his paintings. In the series of paintings I'm gonna talk about, this one is Let All Blues Rejoice. It's one of my favorite ones, and we have used it all along the collaboration we had as a kind of an emblem, a poster for the exhibition we organized. And as you see on the next slide, it's time I present Reg Alcorn himself. You don't see him very well on the picture because he has in front of him this magazine, so in which we published a paper about this artistic work and about the mathematical ingredients that are used inside it. And so on the cover, it's the same painting as before, and the original is just behind him. So you see very different colors, but I think this comes from the Enlightenment, which is different on the several photos. So what I'm going to talk about is more or less what appears in this paper in the magazine like Gazette de la Société Mathématique de France, which appeared last year. There will be soon an English translation of this paper in the magazine of the EMS, the European Mathematical Society, which should appear at spring or summer this year. So let's see Reg from a bit closer. Here you see him better. You see that he was not born yesterday, but what's very interesting to say here is that he was born not far from here in Zambia in the 50s then. So I've been knowing him now for 14 years and knowing him quite well. I'm not at all surprised that he developed a passion for painting at a very early age, because I can't really imagine him not painting. So after growing here in Zambia, he studied in England, traveled around Europe, and is now settled in France in a very charming little village between Bordeaux and Limoges, the southwest part of France, if any of you knows, where many English people like to come, in fact, because the weather is a bit sweeter maybe than in Great Britain or in England. He has many skills, specifically in music, apart from painting, but he's also very much interested in science, maybe first in chemistry because of pigments for painting, the chemistry of pigments, also insects. And then step by step, he approached exact sciences and even mathematics, as we will see. So he spends a lot of time painting, but he also gives painting lessons. And he takes part into activities of diffusion of science, sometimes with this IREM of Limoges Institute of Research in Mathematics Education. I'll speak just a bit more about that in a minute. So hello, Reg, if you're here. I try to say good things, yeah, not to say bad things about you. So in this talk, yeah, I will say how all this began in the introduction, how he met with Reg and how he came to use mathematics in his paintings. Then I will give a bit more details. I will present in a bit more details the two mathematical ingredients he uses in this series of paintings. And at the end, I'll give you his recipe for making these wonderful paintings. So how did all this began? Well, it was in 2011. I was the new head of this little Institute of Research on Mathematics Education, which is also involved in actions of diffusion of science and of mathematics. And I saw this guy come, Reg Alcorn, introduced by somebody else we both knew. And he told me that he wanted to take part in the celebration of the centenary of the death of Henri Poincaré. Henri Poincaré was a great mathematician, physicist, and philosopher, so who died in 1912. And I was a bit ashamed that I didn't know it was next year the celebration of the centenary of his death. Well, I knew his name by some mathematical theorems, but I had not very good culture in history of math, and I did not know the great part this guy had taken in mathematics, physics, philosophy. He's known to be one of the last person with a very broad knowledge in in all fields of human knowledge. Maybe one of the last, maybe the last. But so I found it very interesting that this artist, who was not very much aware of mathematics, wanted to take part in celebration of a mathematician. And I thought that could be a good medium to make the link between mathematician and a large audience. So we began working together with a little team of teachers and academics in mathematics and computer science. And one of the colleagues in computer science told us that next year it's also the centenary of the birth of Alan Turing. Alan Turing, one of the fathers of computer science and of computers themselves. And there's another coincidence is that they shared together 1 century since Turing died 100 years after Poincaré's death. And even if 1 century for 2 persons shared into 2 parts is not that much, despite of that, they did an incredible amount of things, both of them, on very various subjects. So having this exhibition about them, so with paintings, large paintings like that to illustrate some of their major works, that was really very interesting. So we went on with a collaboration, about mathematics in history of art with several periods and mathematical themes attached to them. So it was antiquities and proportion, the Middle Age and the Arabo-Andalusian pavings, and then the Renaissance and perspective. We also built a high-size camera obscura. Camera obscura is a Latin expression that means black box, more or less. And black doesn't refer to the color of the box, but to the fact that inside the box there's almost no light, except the light that comes through a very little hole on one side. And this is a very old object dating back from the antiquity, which is the ancestor of the camera that we all have in our phones. So it's so tiny in the phone that we couldn't imagine getting into it. But then we had this huge camera obscura, 3 meters by 3 meters by 3 meters, where a dozen people could enter and feel what it makes to have everything reversed, right to left and upside down, as you can see here. And speaking of symmetry and things like that. Okay, and also Reg was hired by the Mathematics and Computer Science Department in Limoges to make paintings to illustrate the various domains of research in computer science and mathematics in Limoges. So I had prepared a specific slide for these paintings I liked particularly, but if I begin speaking about it, I think it will take all the time of the talk. And it's not the subject I announced, I'd better skip. So in French, it's le petit déjeuner de Poincaré, namely Poincaré's breakfast. And it's a bit strange, maybe at first sight, the fantasy of the artist, but I find it very deep that it alludes to Poincaré's conjecture, which is about hypersurfaces in dimension 4. And for me, it was an impossible challenge for the painter to represent something of dimension 4 in a two-dimensional painting. Of course, thanks to perspective, you can represent objects of dimension 3 on a painting, but dimension 4, how do you do that? And here, with this object flying in the sky, like if there had been a storm on Poincaré's breakfast, taking them in the sky, you feel that time is passing, they're gonna fall down, there's a movement, and for me, it makes the fourth dimension, the time dimension come into the painting, and he manages to have 4 dimensions appear in a way. But after all this work with mathematicians, in which Reg spent a lot of time reading mathematics at several levels and watching videos. So he really enjoyed watching talks on YouTube about mathematics. He felt a desire for geometry. So many artists have had such a period in their career. Of course, I don't present you Picasso and the Cubist movement, Mondrian, Kandinsky, Vasarely, Morley. And so Reg Alcorn is a bit less well known than these guys, but he also at some point wanted to have a geometric process that would give a structure to his paintings in the series of paintings that he would call transitions. And you have another example of one of these paintings here that I like very much as well. Maybe it's time that I say that some people, when they see Reg artwork, they say that they could guess he was born in Africa and raised in Africa because of the colors, of his choice of colors. So for you, many of you are from Africa. I don't know if you share this feeling. Well, you'll see more of them at the end. So to fill in this desire for geometry, he picked into some of the mathematical objects he discovered when working on the formal collaboration, and there were 2 of them that appealed very much to him. Very simple, but a bit old one, the Truchet tile, which is just a square tile with 2 colors separated along the diagonal. And another one, more recent and more complex, Ulam spiral. And so in the next 2 parts, I'm going to present both of these mathematical objects from an historical point of view and with a bit of mathematics as well, but normally quite elementary mathematics. So we begin with Truchet tiles that are named after Reverend Father Sébastien Truchet. You see, from the second half of the 17th century, beginning of the 18th. So I don't know if at this time there were many professional mathematicians. I think there were very few of them. And Truchet himself was a mathematician, but also many other things. He's maybe well known as most well known as a typographer because he designed a very rigorous and precise police of characters for printing at this time. But as you see, he was also clockmaker, great canal specialist, inventor of countless machines as cannons, tree transplanting machines. It was the time when the Château de Versailles was built in the south of Paris, the new castle for the King of France. And the king wouldn't wait several years to have the trees grow in the garden of the Château de Versailles. So they had to take adult trees at some places and to transplant them in the new park. And this was made possible by this machine invented by Truchet. So also sundials, including the famous mechanical tables of Marly. As you see, this is a quote. It's not that famous for me. These mechanical tables of Marly. There'll be a list of reference at the end of the slides if you ever want to have more information about that. So, being all these things, maybe he was not so much well known as a mathematician, but sometimes several of these activities could occupy him at the same time. And so at some point he was visiting a canal near Orléans, since he was a great specialist of canals, by order of His Majesty the King. And near the canal he discovered a castle with a stock of tiles, of square tiles, divided in two parts by the diagonal, with one half white and the other black. And seeing that, I think he had two different things in his mind. Which kind of ornamental paintings could be done with these tiles? And you will see further that many very nice things can be done. So this is more the artistic way of thinking, but also a mathematical way of thinking. Let's try to count how many different drawings we could make with these tiles. So of course, when you're a mathematician, you begin by a simple case. And so his question was, in how many ways can we arrange two of these tiles together? So let's begin by the simplest case. And he wrote a study, a combinatorial study, which appeared in the Mémoires de l'Académie Royale in the beginning of the 18th century, which was studied by some authors in the 80s, so not so far behind. And they say that this treatise is of considerable importance, I suppose, in the history of mathematics. For it is in essence a graphical treatment of combinatorics, subject that, under the influence of Pascal, Fermat, and Leibniz, was at the forefront of mathematics at the time. So, well, being compared to Pascal, Fermat, and Leibniz, that's not bad, even if Truchet is not as, of course, not as much well known as them as a mathematician. And so, yeah, let's see this graphical treatment of combinatorics, which appears maybe in these tables, which come with his treatise. Of course, in the treatise, he explains what he does with sentences, but these tables give a good view of how he studied this problem. So he wants to find all the possible ways to arrange two Truchet tiles, one side by side. And so in table 1, you see at the top rows the 4 possible orientations of one Truchet tile. So for each of the two tiles, we have these 4 possible orientations. And once you've placed one tile, the second one can come on either one on each of the 4 sides of the first one. So he organizes his study in columns. And in this first table, the two tiles are differentiated. Maybe you see that there's a black one and a gray one. In each column, the black one is always in the orientation of the tile at the top of the column. And in each box, the second tile, the gray one, takes all the possible position as regard to the first one, so to each side, at each corner of each box. And on each line, the gray tile takes one of the four possible orientations. So with this way of presenting his study, he more or less proves that his study is systematic and that he has all the possible solutions, so 4 by 4 by 4, 64 possible solutions, if you consider that the two tiles are different, which was easier for this particular study. But then in table 2, he says, well, in fact, the two tiles are identical. And so putting the black and then the gray, or the gray and the black, if they are in the same orientation, gives the same result. So you don't really have 64 combination, but only 32. That's in table 2. Then in table 3, another reduction is that, well, when you want to use this for paving, you don't really care if it's presented vertically or horizontally. So identifies the configuration which are equal after rotation, and you see that there remain only 10 of them. So that's the main result he gets in this treatise, and this was presented also in an item of the Encyclopédie of d'Alembert and Diderot, which appeared a bit later. It's an item written by Diderot himself, who presents Truchet's reduction, and he goes a bit further. He proposes one further double reduction. He identifies the configurations that are identical when you invert colors. You put black, you exchange black and white. And also those who are identical by flipping. And he explains that those that are identical, well, some imagine they are drawn on transparent paper, and some you see from below are the same as the other one you see from above. This is the flipping. So with this last double reduction, Diderot finds that there are only four possible configurations, and he wonders whether there was a faster way to reach these four configurations, faster than starting with 64 and making successive reductions, as if it was an open question to mathematicians of the time, which is a bit surprising because with nowadays knowledge, it's pretty easy to find the four configuration of two identical tiles up to rotation, inversion of color, and flipping. So you may try, and I'm sure you will find these four configurations. Okay, I think, yeah, I presented also some of the ornamental pavings Truchet proposes in his treatise using the configuration I presented before. There are 7 plates of drawings like that. The first one maybe with the simplest motifs. Here it's the fourth one where they are a bit more elaborate. I've also put the sixth plate to the left, and you see that it becomes more and more sophisticated. And to the right here, this plate is from another book written by another priest of the same religious order called Reverend Doua, who took on Truchet's work and proposed other ornamental pavings designed the same way with Truchet tiles as well. And I found some of those quite modern, in fact. So I was surprised to see that in a book of the 18th century. So here are a few of the drawings that you can find with Truchet tiles, and many more can be imagined. So anyway, with this very simple thing, square divided in two by diagonal, you can produce such complicated ornamental pavings. Okay, so let's skip to the second ingredient, spiral, Ulam spiral. Ulam was a Polish mathematician from the 20th century. He was Jewish and he migrated to the USA in the 30s with his brother. Here he was quickly recognized as a very brilliant mathematician, and he was asked to take part into the Manhattan Project, you know, this secret laboratory in the desert, somewhere in the desert in America, where hundreds of scientists were together to build the American atomic bomb. Maybe some of you have seen the movie Oppenheimer, which went out recently and which tells his story. I think Ulam is not, does not appear in the movie Oppenheimer. Maybe he's not one of the stars of the movie, but he still had a very important contribution to the development of the H bomb. The one which was used in Japan, in Hiroshima and Nagasaki, was the A bomb. So, but another one was developed, so hydrogen bomb certainly, and there were theoretical difficulties at start, and Ulam made a decisive contribution to overgo these difficulties. Well, he also had an important contribution in many areas of mathematics. And the spiral, Ulam spiral, is a bit out of the scope of his usual search. In fact, he was attending to a conference in 1963, a very long and very boring conference. But at the time, he didn't have a smartphone with internet. So yeah, he only had a sheet of paper, and he began to draw a grid on this sheet of paper. Maybe he had in mind to work on a chess problem. But then he changed his mind, and instead of having chess problem, he began to number the intersections of the grid with one at the middle, and winding the integers around one in a anti-clockwise direction. Then he circled the prime numbers. I will recall in a minute what they are. And he was very surprised to see that these prime numbers seem to have a tendency to form lines parallel to diagonals. So let's see this on this part of Ulam spiral. You have one at the middle, and you wind the following integer around 1, 2, 3, 4, and so on, here until 64 at the top left over there. And then you, yeah, these numbers are put on a grid, so it's kind of a square spiral. And then prime numbers are circled. So what are prime numbers? An integer, say n, you can always write it as 1 times n. And usually this proves that n has 2 positive divisors, 1 and n. Unless n is 1. So he has only one divisor in this case. But any integer larger at least 2 has at least 2 divisors, himself and 1. And prime numbers are precisely those who have exactly 2 divisors. So 2, 3, 4, not 4, 2, 3, 5, 7, and so on are prime, whereas 4, you can write it 2 times 2. So it will have 3 divisors, 1, 2, 4, and so it's not prime. Well, you can see, for instance, 3, 13, 31, which is the beginning of a line parallel to a diagonal. It's even a diagonal here. This line won't be necessarily full, will not necessarily consist only of prime numbers. For instance, 57 is not prime. Or to the other side, 5, 17, 37. But the next one will not be prime. It would be 65 divisible by 5. To the other side, you have 1, 9, 25, 49. None of them is prime. 1, we said, it's because it has only one divisor. And 9, sorry, is 3 to the square, so it's divisible by 3. 25 is 5 to the square, divisible by 5. 49 is 7 square. And we'll see this number reappear shortly after. Okay, so Ulam made this observation on this sheet of paper, but this was not quite enough to have a mathematics theorem. So when he went back to his laboratory, which was still the Los Alamos laboratory, he worked with two of his colleagues, Stein and Wells, using the computer of the laboratory. I think there was only one at this time, but a very powerful one for this time. And with this computer, they were able to draw Ulam's spiral until 65,000 for this one, with prime numbers in white. This computer, I think, didn't have a printer, but it had a screen, and I took a picture of the screen, which is this one. And you can see some lines. So this confirms the first observation of Ulam, maybe like this. Well, lines parallel to diagonals here and there. This picture appeared in a large audience magazine called Scientific American in a paper written by Martin Gardner, a well-known popularizer of mathematics, which explains the work of this discovery of Ulam and his collaborators. And maybe it was the first time this question of the question, the very deep and fundamental question in mathematics of the repartition of prime numbers among integers was, so this question was presented to a large audience with a flavor of mystery, since in Ulam's spiral there seemed to be kind of organization that appeared. In fact, it's not that mysterious at all, since in their research paper, which appeared as this one in 1964, Stein, Ulam, and Wells explained that these alignments are due to the fact that certain functions of the integer take many prime values, such as Euler's formula, and I'll say a word about it, which explains for these two lines. And they also identify a function which explains for this one. So now I'm gonna explain how this line appear. So there's just there's a bit of mathematics. There'll be a bit of mathematics, but not too much, I hope. Let's look first at this wider or smaller version of the Ulam spiral compared to that of the photo. It goes to 225, which is 15 square. And you see that when we stop the Ulam spiral at the square of an odd integer, the picture we get is itself a square. So yeah, it stops at 15 square, and if you count, you could check that the size of the square is 14. If we had stopped it here at 169, which is 13 square, what we get is a square of size 12. If we stop at 11 square, 121, we get a square of size 10, and so on. So let's admit this is true, and so more generally, we see that on the diagonal pointing to southeast, the numbers that appear in the spiral are the squares of odd integer, namely of the form 2n plus 1 square. I'm sure all of you know this usual algebraic identity. 2n plus 1 square is 4n square plus 4n plus 1. But we also know that if we stop the spiral at this number, we get a square of size 2n, and so with that we can deduce the expression of the other corners of the integers at the other corners of the square just by subtracting 2n to the first expression, and we get the expression of the corner of the integer of the corner in the direction southwest, northwest, and northeast as here. This is almost all that we need to know. Now to explain how the Ulam, the Euler's formula appears in the spiral. But what is this Euler's formula? It's this function which to an integer n associates n squared plus n plus 41. So a function is like a machine. You feed it with the integer n, and it computes n squared plus n plus 41. If you put 0 in it, you get 0 squared plus 0 plus 41, which is 41. If you compute at 1, you get 1 squared plus 1 plus 41, which is 43. At 2, 2 squared plus 2 plus 41, which is 47. At 3 square plus 3 plus 41, which is 53. I won't go on much further, but all these values I've computed, maybe some of you have noticed that they are all primes. And in fact, Euler's formula is well known because it produces 40 distinct prime values at the integers between 0 and 39. It dates back to the middle of the 18th century, and in fact, it held the world record of the number of prime values at consecutive integer until the end of the 20th century. It was only beaten in 1928, and the current world record dates back to 1989 with 45 distinct prime value at consecutive integers. So Euler discovered this at the middle of the 18th century, and Stein, Ulam, and Wells were able to compute with the computer that when you look at the values up to 10 millions, almost half of these values are prime numbers. The values of this formula up to 10 million, well, 47.5% of them are prime numbers. And so it will make many white spots in the photograph we've seen above. And hence, if these values were on a common line in Ulam's spiral, that would explain for one of the lines maybe that we have seen. In fact, all the values of the Euler formula are not on only one line. There are both cases. The values at the even integers and the values at odd integer are going to make two different sets, and two different lines will appear. So the values at an even integer is e of 2n. So you easily see that you get 4n squared plus 4n plus 1 plus 40. And I'm going to tell you very soon why I cut it this way, why I put the 40 apart. The values at an odd integer are of type e of 2n minus 1. And again, with usual algebraic identity, you find that this is 4n squared minus 2n plus 1 plus 40. So I put plus 40 apart in both formulas because this expression in purple, we have already seen them. I don't know if anyone in the room can recognize them. They were the expression of the corners on the northeast diagonal and on the southwest diagonal. Now you can see them. And what happens if I want to plot the values of Euler's formula, say, at odd integers with the first formula, I know where to place 4n squared minus 2n plus 1, since it's on the northeast diagonal. And from there, I just have to move by 40. Remember that we turn counterclockwise in the spiral, so I have to move by 40 to the left on the side of the square here. If this side is large enough, namely if 2n is larger than 40, then I get a point somewhere on this side. as you, oops, sorry, I went the wrong way, as you see here. And this is gonna, and it's gonna be the same for each integer n. You will go up along the diagonal northeast and shift by 40 to the left. And so you're gonna get a line which is parallel to this diagonal northeast. Exactly the same appears with the values at even integers, but you start at 4n squared plus 2n plus 1 on the southwest diagonal, and you shift by 40 to the right. If 2n is larger than 40, you stay on this side of the square, and you obtain a line which is parallel to the southwest diagonal. And also the other polynomial function that Ulam and his colleague have identified with a high rate of prime values is this one, 4n squared plus 4n plus 59, which is clearly 4n squared plus 4n plus 1 plus 58. And then you just have to shift by 1 to the right and 57 up. And you get a line which is parallel to the southeast direction. Okay, so that's the theory. And in fact, in practice, you can experiment it with a modern computer program. You can have all these values plugged into the spiral of Ulam. So here in red and blue, there are the values of the Euler formula with the prime values in red. And in orange and green, the values of this other polynomial. So we get these lines we had seen on the photography by Ulam and his colleague. What we also see is that for Euler formula, there are two different lines that appear, as I said. In the middle, it's a bit messy. The points seem to have no real regularity, and at some point they're getting a bit more organized. You see the first line here, maybe, oh, not that much. The first line here, another line here, and then this line that, in fact, will go on until infinity. Same thing to for the other part of the Euler formula, and for the orange one, you have got this infinite part preceded by this line, this other line, another line here. Well, and it's a bit messy at the middle. So this is what I've been working about with Sophie Marquez, who is present, studying how this thing occurs. And we are able to show, in fact, at which time we get this infinite part and what will be its slope, and find other amusing properties of these things. Okay, that's all for mathematics, fortunately, maybe. And I think I have a bit more time to speak, to tell you Reg's recipe, if it's okay. With what does he do with all these ingredients? Well, so we have the Truchet tile in the four possible orientations here, and this was not enough for Reg, so he added two more tiles, a fully black one and a fully white one. Well, and it's convenient to give them names or letters, A, B, C, D, for the original Truchet tiles in the different orientations, K for the black one and W for the white one. Sorry. And then among these tiles, Reg chooses a sequence of these tiles of any length, maybe 5, and maybe with repetitions or not. For instance, let's say that it chooses D, A, A, D, B. So D is the first one, followed by A twice, D again, and B, which makes this stripe appear. But of course, so this is D, A, A, D, B, but of course, Reg doesn't put the tiles in line like here, because then he would not use Ulam spiral. Instead of putting them in line, is gonna wind them in a spiral, like Ulam spiral. So this is D, which he puts at the center. Then A, the first A is gonna be placed just to its right. The second above. Then the second D will come to the left. Again to the left to place B. And this is how looks the first occurrence of the sequence winding in the spiral. And then it goes on, repeating the same sequence. So we're gonna go down and then to the right with, so this is D, A, D, B. After that, we go up and then to the left. A bit more to the left and down, we get a rectangle. And we're going for the next occurrence, we're going down, then to the right, and since the sequence is 5 long, we're gonna have a square of size 5 by 5. We can go on like that. So this was with 5 occurrences of the sequence. With 20 occurrences, we get this square of size 10 by 10. And it's quite stunning, I think, that with this very simple process, these very simple objects, we get something that becomes very quickly very complicated and completely unpredictable. And so the game for Reg was to fill in pages and pages and pages of notebooks with different choices of the length and of the content of the sequence to get many of these motifs. And when one of them appealed to him, he transformed it into a painting. So I said a word about how he does that also. But before that, let me show you what we can get with other sequences. ABCK and ABKC are very close, just the two last ones are exchanged, and the results are quite different. And the last one, and the third one, WWWWW, many right tiles, so it's a bit whiter, of course. These ones are quite more regular than the former one, because the length of the sequences are either 4 or 8, and one can show there'll be much more regularity in that case. As you will see in one of the paintings I show you very soon, Reg has been using sequences of length for some of his paintings. I think you will recognize this kind of regularity. But now the question, so this was the geometric part of Reg's recipe to get the structure of his paintings. So now the question is, how do you, what do you do for coloring that? And this is where I'm going to speak of something I don't know at all or very little about it, what Reg told me, which is certainly just a part of all that he knows, and even less than that only of what I understood when Reg told me about it, which is really little. So I won't take much more time. Just to say a few things. The basic rule is quite simple. I think I understood the first rule, the main rule very well, is that you're gonna, since you have black and white, when you want to transform that into a painting, you're gonna choose 2 colors, maybe red and green, 2 complementary colors, and one will go to the black parts, and the other will go to the white parts. But of course, it can't be that simple. Mathematics can be very binary, but painting is not. And so, starting with this first rule, it's gonna get more complicated. Maybe at some points, the painter will get a bit bored with always the same red, the same green, and he's gonna replace one of them by some combination of them two, by mixing the 2 colors at some places, or by painting one above the other make another effect. Maybe also because it's a very precise painting that he uses to make very fit borders, and it takes a lot of time. So I think his brain has a lot of time to think about it, and maybe sometimes spending a lot of time looking at these things. There'll be a shape somewhere that he wants to put forward, and he will maybe say, okay, I forget my first rule now. I use a new color to put this shape more in to make it more visible. Hotter color or colder color, I don't know. Maybe in a wide zone, the original colors will be replaced by others. Well, in fact, he has this geometric structure at the beginning, and some kind of rule for choosing the colors, but very quickly it's inspiration that will be the main rule. His inspiration, and of course his great experience of coloring. Since he's been painting since he was very young, he of course has a very, very good experience of coloring, and he knows how to produce special effects by the choice of colors. So what are the results? So a few paintings to finish. This one in quite soft colors, maybe. So here, I don't know the length of the sequence. It doesn't look exactly like a sequence of length 4, but I don't know. I think it's much more apparent in this one with much hotter colors, very lively colors. For me, it looks very much like the example of length 4 that I've shown you. And of course, you see that there aren't only 2 colors. There are many more than that. The rule is never completely followed. So this is one of my favorites. It's all these paintings are around 1.2 meter by 1.2 meters, so smaller than here, of course. And when we put this in we organized an exhibition at the library of the Faculty of Science in Limoges just before the COVID, in fact. When we put these paintings on the wall, it was quite impressive for me that the colors were kind of vibrating, and when you were at a certain distance from this painting, it looked as if some of the colors were at the background and others at the foreground, like if this painting had been a 3-dimensional object and not only 2-dimensional. So that's yet another way to add dimension to a painting by the choice of color. Very, very impressive, this one. And just this last one to say that among the hundreds of paintings he realized in this series, there have been variations even to the geometrical rule. Here, the Truchet tiles that are square tiles are replaced by rectangular tiles with other effects that are produced, visual effects that are produced. Okay, I think I've said the most of what I wanted to say. So as I said, there's a little list of references. For some of them, there's a link to the internet, for instance, for the encyclopedia, also for the treatise of Dominique, of the Father Dua, and for, I think, the treatise of Sébastien Truchet. And this is the title of the English translation of our paper that is to appear. So thank you very much.
Very much for a great talk. Thank you very much. Other questions for our speaker? Please, Surab. The microphone is coming. And then we will ask also our online audience to ask questions if they have.
Thank you very much. It was a very, very interesting talk. So one thing that is kind of in common between Ulam's spiral and the artwork is this emergent patterns that are kind of local, and some of them don't go to infinity. Even with the prime numbers, when you showed us the first few numbers, there were some lines which later disappeared when you zoomed out. Is there any mathematical theory of this emerging? Because one begins with a sort of pattern in the case of the art, since the same sequence repeats, right? But then the other patterns that emerge that seem to be independent of that. So is there some mathematical theory of these emerging patterns that brings together the artwork and the prime numbers?
That would be nice. I don't know about that. It seems complicated anyway. Where when you draw these spirals, you see really unexpected things. Well, there are some. You can see some motifs that repeat from place to place, but clearly it won't be very regular. There will be many irregularities. It looks like something very chaotic. So maybe there are ways to explore that, but I'm not aware of these ways.
And if I can ask a second quick question, in the work that Truchet did to count these things, I guess today we know these numbers for grids of arbitrary size. Is that true?
I'm not sure. You mean the number of combinations?
Yeah,
if you had 3 tiles, 4 tiles?
If we have a grid, the number of ways we can tile it, which is
for each tile can be in four possible orientations. So if you have n tiles, you get a 40.
Yeah, but taking into account the flip and the things that you.
Wow, that's a hard question. But don't you have easy questions?
So combinatorics haven't looked at that?
I don't know. I don't know. Well, combinatorics can do a lot of things. And I know just a little bit of combinatorics.
Okay.
I don't know, really.
Thank you. Thank you.
You're welcome.
Other questions? Do we have questions from our online audience? Maybe I have a stupid question. At the beginning, you mentioned also the work of Vasarely and others. Did they have an algorithm, or did they paint just out of the head?
If you ask a question about arts, I can give you my feeling, but it's not really knowledge.
What is your feeling?
Well, I've read that Picasso represents things as they can be seen from several directions, kind of thing. I don't know for the answers.
Hi, Prof. There were some questions online about the slides and availability. So I just want to remind everybody that these slides will be uploaded to the NITheCS YouTube channel. So anybody looking for the slides, please welcome. They will find it there. Thank you.
Okay, if there are no other urgent questions, we will have the... here we go. Sorry. Please.
Thank you for the talk. So just a small question. Some of the last representations of the tiles, when you were choosing the words to build them,
the sequence, yeah,
the segments looked a bit. And when you repeated a big square, they looked a bit like modern QR codes. Just from the book, without the colors, I'm just talking about the square.
Yeah.
So I do have a question. I mean, QR codes are generated using finite fields, and they also parameterize information. You can encode data in the positions of each of the pixels in a QR code, and some you have like repetitions, and I mean there are several things you encode in a QR code. So of course the question is obvious now. Do you think you could use maybe some of this to encode information and maybe perform some code this way with colors or not?
It certainly encodes the information of the original sequence you want in a spiral, but I'm not sure it can encode much more than that, since you start with this and I don't know, but I've not tried to apply my QR code app on that. I don't think it works. Yeah. Maybe you can find Euler's formula somewhere, since you use the same winding as the integer. I don't know.
If there are no more questions, then let's thank our speaker again. Thank you very much. And before we conclude here, a little thank you from us. You probably know it from Sophie.
Yeah.
So